course is kind of winding down, so today we're going to talk about the Big Bang cosmology, and mainly we've talked a bit about redshifts already, but the other pillar of the Big Bang is, of course, the CMB, and so that's going to be the preponderance of our discussion today. And then Thursday, we'll wrap this up with a look at cosmologies and try to ask the question of whether physics is really the best discipline to be approaching cosmology in general. And we'll try to look at the way that some different cultures across the ages have approached cosmology in different ways than physics. And we've hinted at some of that in the past, but there's something to it. Something more to it, I should say. All right, so guys, help me remember what we talked about last time, where we stopped. So yeah, so last time we talked a good deal about redshifts. Whoever I'm going to call on next wants to think some more about redshifts and remind us a bit about that. But yeah, in general, as we get really far out in distance, when we see things that are really far away, that is, they're really dim, we see that they're highly redshifted as well. And so there's a number of things actually that can redshift light. Not the least amongst them, which is condensed matter chemistry, but also Doppler effects, right? Things moving away from you. And this has, of course, been interpreted cosmologically for these distant objects, that the whole universe itself is somehow expanding. This is the most popular interpretation as of late, although there's some issues with that, which we'll talk about. But I think what you're getting at is that we don't really have a mechanistic model for light. In other words, we don't really know what atoms are doing to each other during this mysterious process called light, even though we're all subject to light all day long. In fact, we have a hard time even thinking without speaking in visual metaphors about stuff. So light is absolutely central to everything we do, but don't really have a mechanism for it. And I think I like that you brought up that light is a conversation between atoms. You know, this idea was actually really pointed out by Gian Lewis, who was this complete super boss in chemistry that gave us essentially the idea of several ideas in chemistry. Since this isn't a chemistry class, I won't bore you with them, but he had this idea that light was being treated by physicists as if it was just this magic ball of energy that was shot off from an atom. And he thought that was unreasonable because you never ever observed light without having at least two atoms involved. And so this other gentleman at Caltech, kind of working off of Richard Feynman's ideas, started approaching light as a conversation between atoms. And he imagined that actually as the light is emitted from one atom, there's something taking place at the other atom at the same time. It almost implies the atoms are connected to each other in advance. And so there's actually something happening that's mediating this transaction. At any rate, without a really good, solid basis of understanding what light is, it's very, very tenuous to make assumptions about interpreting the different colors of light, especially as they travel across billions and billions of light years. And so I think, you know, it's completely reasonable that at this point in our discussion we have no firm answers about these huge questions. I mean, it's really hard for us to imagine 14 billion of anything like grains of rice or pieces of sand, or 14 billion people, right? That's almost twice as many people as are on the planet. It's hard to conceive of these kind of distances. And that's how many light years, right? And how fast light is. I mean, we're making these statements about enormous, enormous scales. And so I don't think it's unreasonable that we're not there yet. But figuring out light's going to be a huge step in the right direction. All right. I mean, one thing that's really interesting about the Big Bang is that as a theory, this has kind of been the most disturbing thing for me all along, is that it's completely logical to take all these redshifts and deconstruct them, and we'll talk about that. It's called the Hubble time, or the Hubble principle of basically running the movie in reverse. So you see all of this redshift, you assume it's motion of the distant things moving away from you, and then you run the movie back in time and you get to this point. And if you run it back far enough, you get this really, really dense point, right, where everything's kind of smashed together. The difficulty, as far as science is concerned, is that in science we always have to provide some sort of mechanism for the cause of something, right? Now, the Big Bang can't do that, right? You can maybe say that things look like they started all at this one point, right? But what caused them to blow apart in the first place? Like you mentioned an explosion in one version of this. So people are always trying to come up with these different ways in which that expansion could have happened, that explosion, if you will. But what causes that? It sort of boggles the mind. It's difficult to ask for an answer to that without getting into supernatural or theological arguments. So I don't know. That troubles me anyways, and I don't know if it bothers anybody else. But I think what we're going to see today is that as we move through, this redshift is certainly one pillar of the Big Bang, and there's another pillar. And that's kind of it, really, with respect to the Big Bang. So there's the fact that people really, really want to understand where all of this came from. It's very difficult. For some reason, when I talk to people, let me ask you guys, does it make more sense to you intuitively that the universe should come into existence at some point in time, or that that wouldn't be necessary? Let's say the universe could have always been here. Which one makes most intuitive sense to you? I'm just curious. Show of hands. A birthday for the universe. Does that intuitively make sense? Couple people? That the universe may have always been here. Is this intuitive to anybody? A few more of you, actually. That's surprising. Maybe because you've suffered through my course already, so maybe I've contaminated your opinions. But it's interesting because this seems to go back and forth. So most of the scientists prior to the 1900s would have been on the side of the eternal universe. This idea that the universe would have a birthday was actually kind of anathema to them because that's what the church was pushing for the previous 2,000 years. And so it seems to go back and forth. Where am I going with this? It seems that at least in our current society, at least in the culture I grew up in, it was very much comforting to people that the universe would have a birthday to it. So as far as I can see, there's three things the Big Bang has going for it. One, people really want that birthday for everything because it's self-similar to their own lives, or they just intuit that it's correct. There's the cosmic microwave background radiation, which we're going to pick on today. And then there's this redshift at a distance business. There's also some arguments about the elemental abundance, which I'll address as well, but I'm not sure that anybody's really holding that up as a banner for the CMB at this point. There's some different ways to talk about the elemental abundances. I think it could actually support either theory. So I guess what I'm trying to say is that this is actually pretty exciting for everybody. I hope that you guys will understand that this is a very important, well, in so much as science is important, this is a really important moment in the history of science because I think we're at an interesting crossroads where, this one theory was championed for 50, 60 years. There's a lot of problems cropping up with some of the main legs of that theory. And so I think it's interesting, maybe you guys can just weigh that out on your own and keep that in mind. The textbook does a pretty good job of bolstering the Big Bang Theory and giving you evidence for why it's reasonable. I'm going to try to sort of counterbalance that with some problems, especially with the CMB. But I also want you to think about the redshifts in a different light as well. There might be many, 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 many reasons why light would be shifted after billions of years that have nothing to do with Doppler expansion. Yeah, quasars are an interesting piece of the puzzle, especially since they're often held up as evidence of really distant objects. There's a lot of conflicting information about quasars. But in general, I think it's tricky because for most people, this idea of redshift, when you start thinking about redshift beyond mere Doppler effects, right? So beyond just recession, it gets into a really technical realm, right? You're talking about you're talking about the way in which atoms interact with each other across, as light is relayed from atom to atom across great distances. Like, these kind of experiments haven't been done because you're talking about such enormous distances. It's a very difficult thing to qualify because the only place that we're able to observe this kind of enormous redshifts are at these extraordinary distances. So it's like, this is a very, very difficult laboratory to run because we only have one example of it, and it's things that are really, really far away. And we don't really know why that's happening. Of course, the Hubble idea is that space itself is expanding. I think I've picked on that enough, but it's a bit dissatisfying to me, especially when you think about space being defined as essentially distance coordinates. I'm not sure that saying that, you know, I'm moving away from you right now, if I was to walk in the other direction, is really, you know, necessarily to be explained by the space between us increasing, right? Moving away from you because I'm walking away from you. So there's actually a mechanism underneath that. I think it's a little bit of a problem being packaged as a solution in my estimation. But we'll see. I mean, there might be something really interesting happening in terms of the way that light loses energy across distance. So the CMB has it actually points at there's some alignment of the light in there, which points to the fact that it had some directionality to it, that it originated at some point. So you can do some math very similar like you do with the Hubble expansion and compare these two. Now, I'm going to pick on that a bunch today because the problem is that if you use these same anisotropies, these same inhomogeneities, these same sort of differences, and you try to correlate them and point them back at a point, they actually align with a lot of local structures too. So they align, there's alignments you can find with respect to the plane of the ecliptic, so where all the planets are located. They seem to align with other observations of distant galaxies and supernovas as well. And so it almost seems like we're carrying the CMB around us. And so let's hold that thought because I'm going to point out a few different interesting examples of that. But what is interesting is even if you do that math and calculate the age of the universe, you do get a different age than you get from the Hubble expansion. Now they're not super different, but they are really, really, how do I say this? The values that you get are not so far off from each other, but they are really tightly constrained in their differences. So you get a very, very accurate number with one, and then you get a very accurate number with the other, and they have no overlap whatsoever in terms of their standard deviations and so forth. So that's a bit troubling to people. Okay. Somebody else had a point, yeah? Yes? Yeah, I mean, I think the point that you bring up that's maybe like generally relevant is that our entire, like, this is hard to impress upon you guys, and it seems ridiculous, but it's true. Our entire cosmology, right, is tracing back to Einstein and perhaps back to Newton before him, is entirely based on this. I mean, I'm going to get in trouble for saying entirely, but the preponderance of the modeling is based on gravitation, right? So when we see something moving somewhere in the night sky, we think that's because gravity is doing that, right? Almost 100% of the time, right? Why are these objects expanding, moving away from us? Shouldn't gravity be holding them together? Well, there must be some dark energy that's pushing them apart, right? Every single anomaly and every single phenomenon in the night sky is more or less attributed to gravity. Why do stars glow? Like, why do stars evolve and die the way that we've talked about them doing under the standard model? Well, it's because gravity is causing them to collapse and so forth. Everything comes down to gravity. Now, it may be true that gravity is a huge player, but of course, we know very well that gravity is actually one of the weakest forces in the universe, for sure, right? Like, you know, for instance, if I magnetized a paper clip right now, I could lift it off with a very weak current, actually. I could drive a little current through, like with a AA battery through a little piece of copper, and I could magnetize and pick up a paper clip. So I would absolutely destroy gravity, no problem, right? Gravity is really, really weak, and it falls off with an inverse square quite weakly. So what about the role of magnetism, of galactic magnetism, about other processes like that, electromagnetic processes that we just don't totally understand? I think the reason that we didn't study galactic magnetism for so long is we didn't have a means to do it, right? The only way to really see it is looking at how grains of dust are being polarizing light, how they're orienting, realigning with magnetic fields. And it's not like galaxies have just one nice, pretty magnetic field. They have all of these different nested magnetic fields, and it seems to obscure what's actually going on. So yeah, there might be a huge role for magnetism, electricity. Of course, the sun is, if you look at the surface of the sun, I usually have a big picture of it up before class. There's these beautiful magnetic structures, just it's so intricate and complex, right? I mean, of course, all of those structures are electrically and magnetically active, and there's all sorts of dynamics going on, right? How much of this is playing out and organizing the universe? We don't know. Yeah. Yeah, I mean, you're asking a question about something. Well, the first part of the question was, is there something outside of the universe? Right? So, like, the word universe, it means different things to different people. And I would say, technically speaking, universe means universe. It's like, it is everything, right? So there can't really definitionally be anything outside of the universe. Now, perhaps by universe what we mean is everything that is somehow interacting with each other in one context. And maybe everything in our local network that we can see is interacting somehow. And then there's a completely separate universe next door that's completely cut off from ours, right? Like, kind of the way that people used to think about the galaxies, right? These galaxies were completely isolated from one another. They used to call galaxies island universes, actually. Now, the second part of the question was, could there be wait, can you rephrase the second part of the question?
That if there is something outside the universe, that its gravity is what's pulling.
I see. Could things be being pulled? Well, I think this actually introduces a really interesting point. So, the other definition for universe, and this is the one that's probably more technically accurate for astronomers, is that the universe is everything we can see. So, the horizon of the universe, let's say 14 billion years away, is literally the faintest objects that we can possibly see right now. Now, if that's really what's going on, and the truth is that this place is way bigger than we thought it was, then I think the answer to your question is absolutely. There could be tons of stuff outside of that that's yanking on those distant galaxies and so forth, those quasars, that's pulling them away. And maybe there is some contribution to that in terms of the expansion, or let's say the recession of those bodies away from us. I also think that there's almost certainly some contribution, whatever it turns out to be, of light being affected by traveling 14 billion years. So remember, the lower energy light is redder, higher energy light is bluer, right? So if somehow the light is losing energy by relaying across gazillions of atoms, right? Look, think about it. When the light from the sun comes down and hits your eye, it's not directly coming from the sun, right? It's getting handed off from gazillions of atoms throughout the atmosphere, from one atom in the air to the next and so forth. There's this whole relay process, right? Now, if light's traveling from 14 billion light years away to your telescope, it's got an uncountable number of relay steps involved in that, right? That seems to me, at least intuitively, to be plenty of opportunities to lose energy, right? In other words, to redden. So I don't know that people have, well, I'm sure that nobody has made a convincing case of exactly how it reddens, how much, to what quantitative amount it's being reddened versus it's receding, right? We can only tell that it's reddening. We don't know what the contribution is. And this idea of light losing energy across gazillions of relays is difficult to prove out because on the time scales of a laboratory, you would never see it. Right? You need these billions of light years, these huge distances in order for this effect to become dominant at all. So, yeah, if the things are moving away, there might be other stuff beyond them that we can't see. If they aren't moving away, we would not really be able to tell the difference because it would look the same as the light losing energy by any other process. So that's the let's say the Big Bang is like a big monster. That's one of its legs, is this redshift at a distance business. The other one is the CMB, which we should probably start moving towards. Does anybody have any more points before we move on? Yes? That's an interesting idea, yeah. Do they so you mentioned the great attractor being this point that different galaxies are being sort of drawn towards. Do you recall if there was a mechanism given for that? Do they have an answer for why that is, why everything's moving towards these points?
I don't think so.
I mean, oftentimes, like I said, the history has been that the reason things move in the universe is because of gravity. And so if you don't see anything pulling on it, then you have to invent some mysterious stuff like dark matter or something to pull it towards there, right? This is almost certainly because we don't understand all of the different forces that are at play in the universe that are moving things around. But yeah, something like that might be playing out. But again, that might introduce more problems. That might just package the problem differently. Although I kind of like that problem a bit better. So that's really interesting. Yeah, the great attractor. Anybody else have any points before we keep cruising? One thing I did want to mention is that I believe your final projects are due this weekend. So keep an eye on that. There is going to be a short assignment, just a short flip grid to do during finals week, but it shouldn't take you more than a couple of minutes. I think it's just a kind of overview checkout assignment. So get that in. And get all of your assignments. If you have any missing quizzes or anything like that, please, yes?
Do we have a final meeting time at all?
No. We're not going to have a final in this class, so don't come to class. What was I going to say? You do get in any missing assignments because I will close those out, not this weekend, but next weekend. Everything that's not turned in will turn into a 0. All right. I think that's the only thing business-wise. Okay. Now, I think we've done a good job of reviewing changes, reviewing the Big Bang theory as it stands. We have this recession velocity. We have this other pillar, which we're moving into today, which is this leftover hiss from the Big Bang, which is called right now the cosmic microwave background radiation. And I'm going to provide a sort of ballast to the textbook and argue that perhaps the microwave background isn't cosmic in nature, that it's actually something more local, something more nearby to us, which is, of course, extremely heretical. But I think it's quite interesting, and if you don't like the presentation, that's totally fine. But I do think there's some serious problems with the data as it stands, and no matter how you interpret it, it might be difficult to concede that it's actually a cosmic structure, that it relates to something that's affecting everything, because, of course, it actually seems to align with individual pieces that are very close by to us, which is troubling. And so, I mean, I think it's really interesting to think about these kind of huge theories and how we should, in some sense, expect them to change very, very slowly. You know, the theory that I'm going to present to you for the CMB at the end of the day, it has been developed over the past 20 years by a man that I have come to know very well. And it's interesting because he was a professor of radiology. He developed one of the most high-powered MRI machines in the world back at Ohio State University for over the course of several decades. Had a really illustrious career there, and then ended up leaving to work on astrophysics. And it's been a really rough road for him since then, right? Because one thing that I've seen happen over and over again, especially just doing this podcast and talking to all these scientists all the time, especially people who come up with new theories, is that people really think that when you come up with a solution to a problem, that everybody's going to be super excited for you, right? It's totally logical. You think, like, you read the history books about scientists, and you see everybody, like these heroes like Einstein and Newton, and you think, if I come up with a really brilliant idea, everybody's going to throw me a party and celebrate my good idea. And unfortunately, that is almost never how it works. And that's very, very painful and tragic for people, because the truth of the matter is that people really become comfortable with paradigms. And it often takes an entire new generation, right? You often have to have your previous generation of scientists die with their paradigm before you can actually get a real change. And that can be quite painful. And I would call your attention to folks like Copernicus, right? So your textbook, it was more last semester than this semester, but they devote an entire chapter to Copernicus and the Galileo story and how, isn't it wonderful that reason triumphed over superstition and the church and all of this? Well, the truth is that Copernicus, who, of course, just to refresh your memory, Copernicus was the one who essentially redrew the solar system, placing the Earth not at the center of the solar system, placing the sun at the center. Copernicus had that idea when he was young, right? Maybe perhaps like 10 years younger than me. He carried that idea around on a notepad in his breast pocket for his entire life. And he would only talk about it with his closest friends because he knew that nobody was interested in this paradigm shift at all. Only when the printing press was invented at the end of his life did he decide to self-publish that idea and have some copies printed literally on his deathbed, right? The same thing happened with Charles Darwin. Everybody loves to talk about Darwin now as if he was this genius who had a brilliant idea and he just went out in public one day and was like, hey, here it is, here's my book. Everybody, I've decided why all of the animals look the way they do. That's not the case at all. Darwin was terrified. The only reason he even published his ideas is because he got wind that this other guy named Wallace was about to publish his ideas out from under him. So he decided to jump on a paper with him and publish an abstract version of that. But he was basically sitting on that thing until he was on his deathbed, right? He was kind of quietly talking about these ideas with people, but it wasn't like this is something that people really wanted to jump on the bandwagon with. And it only took years and years of people arguing about this before it became kind of undeniably a useful theory. The same goes with Copernicus's idea. So, when we talk about different alternative models to the Big Bang and problems with it, sometimes it takes a really long time of problems piling up and of sufficient alternatives amassing before people are really willing to look the other way. And sometimes it takes the death of the scientists who have been championing the previous idea for so long. So that puts us at a really interesting point in history as far as I can tell. All right, so these three pillars we're going to talk about. We talked about the redshift quite a bit already. I mean, again, it's worth reiterating, cosmology wasn't an actual hard science until 1964. That was the discovery of the CMB. So we talked about the Belgian priest Lemaitre basically taking Hubble's data with the redshifts and making a model out of it. That wasn't considered seriously hard science, and Einstein himself didn't buy it when it was proposed in the 20s. That took almost 40 years until people actually discovered that there was this hiss, this radio signal, and I'm going to go through the story of that for you in just a second. Before cosmology was actually assumed and finally made its way into actual science departments, right? That's kind of hard for us to imagine right now because when you think of cosmology, you think of mathematical physicists. That's a very new thing. So there's two pieces to this present cosmological story that underpin it, which are in some sense in great jeopardy right now. One is that the distance ladder is reliable. Now, we've talked about the distance ladder. Does anybody remember what that is? Somebody review for us? It's kind of a complex idea, but it's important. Yes, Will, yeah. The distance ladder in astronomy.
I was going to say it's kind of a series of methods by which astronomers measure cosmic distances, so starting locally with parallax and then moving out with the standard candle stars.
Perfect, yeah. Yeah, and what's interesting about so you mentioned it's sort of this series of moving away from our local neighborhood where we use different methods nearby and we have to rely on different methods far away. And what's really interesting is that they all in some sense are based on, like the parallax measurements we can do are really, really limited, right? We start talking about orbiting binaries very quickly, and even then, now we're talking about having somewhat of a material model for white dwarfs, right? For getting this radial velocity of how big something is, how it's turning, and so forth. But beyond the eclipsing binaries and so forth, you're really moving into theoretical territory where you think you know what a particular star is. You think, it's blinking at this rate. It's probably one of these Cepheids or this Lyrae star, so we can kind of know what it is. We've been wrong about that in the past. Now, when you go beyond that, at some point you're getting into just the point where all you see is redshifts, and you're using redshifts to gauge distances based on the theory of Lemaitre and Hubble, right? So the story assumes that that distance ladder is absolutely reliable. It also assumes that the universe is at least weakly isotropic, so basically the same in every direction. And so the story that's told, based on these three pillars of evidence, the redshift expansion, elemental abundances, and CMB, it is a logical story, right? I don't want to cast any shame on it for being illogical. It's not illogical. But remember what logic is. I think this is like a really important point here. Can anybody tell me what logic is, actually? Before I just dump it in your lap? It's interesting, because we use that word all the time. We're like, oh, that's logical. But we perhaps don't stop and think about what it is. I mean, logic is essentially a very simple process by which you assume some axioms, right? So those are the ways in which a statement is processed, essentially if-then statements. If this happens, then this should happen, right? And you make some initial assumptions about the system, right? Like whatever it is. In this case, the assumption is that the distance ladder is correct, right? If the distance ladder is correct, then when we look out far away, the things that are farthest away are the reddest. If the distance ladder is not correct, then that statement is no longer logical, right? It loses its logic. So you set up these series of gates. And in fact, math is just a very particular form of logic that just uses quantities, right? Where you make if-then statements with quantities. If this number represents 1 and this number represents 2, and you add 1 and 2, then you get 3, right? It's a logical statement. It's a particular kind of logic. So this whole theory is in some sense pretty logical. The problem where things usually fall apart when theories change and paradigms shift is that the assumptions underlying them are actually what turn out to be faulty. So if you'll recall, this has happened several times in our story so far. With respect to the actual distance ladder, for instance, it was originally assumed that two very different types of blinking stars were both Cepheids, right? And when it turned out that they were actually two different kinds of Cepheids, it changed the distance ladder by a factor of 2. This is back in the 1950s with Walter Beatty's work. So these assumptions are almost always what go awry. And the two biggest assumptions underpinning all of this right now, the distance ladder and the isotropy of the universe, the second one is perhaps the more troubling, and we'll see that as we start looking at the CMB. But we've already talked about these large-scale structures. The galaxies seem to be aligned into filaments, right? This is very shocking to people in the last decade or so. It seems like the universe is not the same everywhere, right? It seems to be quite a bit clumpier than we were hoping it would be. So the Lambda CDM scientists, the Big Bang scientists, are prosecuting this theory logically, and I think it's reasonable for us to take a look at that logic. So again, the basic idea is that they look out, they see the things that are farthest away are moving away the fastest. Now this was a huge problem because Einstein pointed this out very early on, that if gravity is the biggest player, and it was really the only player in his theory of relativity, his general theory of relativity, then all of the different galaxies should just kind of crunch down on one another, right? Everything should be pulling on one another. If gravity is just atoms pulling on each other, then why wouldn't we all just turn into a big, clump, a big tangled knot? And so he actually introduced this variable, a little fudge factor he called the cosmological constant, into his theory. And he was actually, if you read Einstein's letters, he was really troubled by this because he didn't have an explanation for it. It was just a number he stuck into the equation that would make things not collapse on themselves, essentially. Now, a bit later, actually, Hubble came along and discovered that, as we've talked about before with Lemaitre, that these redshifts implied that there was an actual expansion. And so he said, Einstein, don't worry about it. The expansion of the universe is counterbalancing gravity, and that's fine. It's really just this explosion, right, from the Big Bang. Now that's kept everybody calm for a little while, but it didn't really hold up in the long run, and we'll talk about that in a minute, but it came down to the fact that actually it seemed like things were speeding up the further away they were. So it's not just this simple explosion, right? It's a matter of things actually, the redshift would imply that things are actually going faster and faster the further away they are. Now, if you use that Hubble expansion rate, like I said earlier, it's kind of like you can deduce a birthday for the universe by running the clock backwards, right? So if you do that, we call this Hubble time. It's essentially an inversion of that expansion rate, so 1 over the Hubble constant, and you get this thing called Hubble time. Now, when I really puzzle over this a little bit, it is kind of an interesting idea that you could see an explosion and then trace it back and run the movie backwards, right? And then project where the hand grenade was at in the first place or something like that. Seems like somewhat reasonable. And you can actually do this pretty accurately for something like pool, like billiard balls, right? Any of you guys play pool? Yeah? It's like if you shoot a pool ball, you can run the movie in reverse, and essentially this is how you calculate where your ball is going to go, right? You kind of run the movie backwards in your head and line up the shot, right? So that works out for billiard balls. But what about something really complex, like an ice cube, for instance? So if I took a movie, if I set up a nice little experiment, it's like an aquarium, right? It's airtight, and I put an ice cube in it, I put a film camera on it. And for some reason, my camera is incredible, and I can actually watch individual water molecules, right? Let's say that I come in a bit later after the ice cube's melted, and there's just individual gas molecules, there's evaporated, there's some water on the floor of the chamber. And I see all of that. Can I take that movie of the back half of this experiment and reconstruct an ice cube from it? Right? It's a little bit tricky. I don't think you could, actually. I don't think that you could take a bunch of evaporated water molecules, no matter how precise you were able to observe them, and reconstruct that they used to be in an ice cube, right? If you didn't actually see them at an ice cube in the first place, I don't think that you could trace that event backwards. So my point is that really simple collisions and so forth, like billiard balls, okay, you can time reverse those and come up with an accurate picture of what happened before, but something as complex as an ice cube, I don't think you can do that with. Now, I'm going to go ahead and make the assumption that the universe is a heck of a lot more complex than an ice cube or a bunch of water molecules, right? So this idea that we can accurately trace back some trajectories that we see today, even if they are trajectories, let's say that they are, let's say these redshifts are actual trajectories, that we could reconstruct the first, femtoseconds of the universe from that is a bit like saying we can take the evaporated water molecules and reconstruct an ice cube from it. I don't think that you could do that. It just seems like that's an enormous act of calculation that would require way too much information and way too much chaos to be able to make sense of. All right, so the problem comes, of course, that the universe seems to, these redshifts imply that things that are furthest away are actually, the expansion is actually happening faster at those points, right? There's more expansion at the more distant reaches. And so, how do people explain this, right? All of these little things that crop up, right, that don't make sense, in some sense, the way that they're explained is that the problem is given a new name, and the name is treated as a solution. So the solution to this problem is called dark energy, right? And this is that there's some mysterious force that actually causes these things to be pushed apart from each other that counteracts gravity. And so that's where we're left at. Now, we already talked about this expansion proposal, that the space itself, the distances between these bodies would be expanding. I'm not going to spend too much more time on this. I do think that there's something really interesting here about this proposal where they use this balloon, right? I think that like a balloon has elastic properties to it, which is quite interesting. Actually, all objects that don't just rupture have elastic properties. So elasticity is sort of like a deformation that's reversible, let's say. And I think that in general, when we look at atoms, and we look at things that are vibrating and resonating, it's not unreasonable to think of them as elastic in nature. And so I kind of like something about this analogy here. Although I tend to think that the atoms themselves actually are perhaps where we should be looking for all of this elastic dissipation in. Again, without a material model of light that actually considers all of these relay steps and how friction might bleed energy away from those rays of light over the ages, I don't think that we're going to make sense of this redshift business. So I think we reviewed this sufficiently at the beginning of class. I'm not going to waste any more time on the redshift. But that's one of the legs of the Big Bang. Now, people, of course, went through various iterations of this Big Bang model and tried to, this was mostly going on, let's say, in the 90s, until people came up with this dark energy idea. All these different, perhaps, possible formulations of the universe. Perhaps gravity would cause things to eventually, the explosion would happen at Big Bang initiation points, and then gravity would pull everything back, so you'd have this big crunch. Or maybe things would just sort of slow down as the explosive power lost its heft. Today, based on this idea that the expansion is actually accelerating, we have the idea that the universe will essentially one day end in this complete heat death, cooling, everything moving away from itself. Now, I'm going to use that, actually. That's quite an apocalyptic cosmology, by the way. So next class, I'm going to try to bring in some different cosmologies from across the ages, right? Now, apocalyptic cosmologies are not uncommon. They're actually particularly not uncommon in civilizations that are sort of nearing their expiration date, which is really interesting. So the alternative, of course, is cosmologies that are more cyclic in nature, right, where things come and go, that forms appear and disappear. But for whatever reason, we have this very death-oriented cosmology. I've heard it said that cosmological science is something of a death cult, right? With all these dark things and dark energies and dark matters and heat death of the universe and all of this stuff, which is not unreasonable. All right, so let's start to think about the glow, right? So the second biggest pillar of this whole story is this cosmic microwave background radiation. And what is that? Let me just summarize it, first of all, and then let's look at the details of it. So to summarize it, what we're looking at is that scientists essentially discovered this black body hiss, right, in the far infrared spectrum, so beyond the visible wavelength, this nice curve of power versus frequency that looked a lot like a black body. They were doing some different communications experiments at the time. They were actually working at Bell Labs, and they found this hiss. Now, people prior to them finding this hiss, this black body hiss, and we'll talk more about why it's interesting that it's a black body in a second. People before this actually thought that you should be able to see some trace of the explosion of the Big Bang. So it was theorized throughout the 40s and 50s that if this Big Bang thing was actually true, and again, most people weren't really on board with it at that point, they figured you'd be able to see some afterglow of it, right? So that idea was kind of already there in the collective consciousness. There should be some evidence of that. Now, people have kind of reconstructed the story naturally that, like, if you run that movie backwards of all of this expansion, you're going to get to a point that's really, really dense, which means it's really, really hot. And so, of course, the leftovers from all of that heat should persist in some energetic signature across time. So I'll come back to the elemental abundances in a minute. The basic idea being that when the universe was much denser, it was much hotter, and it cools as it expands. So we're looking at something much cooler today. Therefore, the afterglow of the Big Bang should have also cooled commensurately, which means it's going to be quite cold. There was actually a number of predictions given for what this hiss should look like, right? Interestingly, is that none of them predicted that it would be a black body, right? And the reason for that is that, I guess I could go back to this previous picture, but the idea was that the hiss should have really appeared when the first atoms appeared, right? So there was just a bunch of primordial stuff. Actually, the story goes that it was just light before atoms, which is really, really difficult to understand because I don't think that there's any evidence for light without atoms. But it is very biblically commensurate, right? You know, and let there be light, you know, light in the beginning, that kind of thing. So I think that's why people liked it. But the idea is that as soon as the atoms appeared, during this, they call it this event called recombination, that this is the really hot event from which we would see the hiss that would be the sort of smoking gun of the Big Bang having happened. Now the problem is, as I hope you're all aware at this point, that these atomized, let's say, ionized atoms, these really individual atoms, they haven't formed into any condensate, there's no molecules, there's no stars, there's nothing. They're just gas, right? And we know that gases don't give us black body spectra, which is really interesting. But nonetheless, when this hiss was detected, in the same issue of the journal in which it was reported, the paper, I believe it's the paper right afterwards in the volume, actually purports that the cause of this hiss is the leftovers of the Big Bang. And makes an argument based on the temperature and the cooling and how much it should have cooled over the last 15 billion years and so forth, that it would be commensurate with it. But what's really interesting is that this hiss was of a black body spectrum. Now, like I said, I'm going to just keep saying it over and over again. The way that you would get that nice black body curve in a laboratory is you would heat up a solid or a liquid. That's the only way that anyone has ever observed a black body spectrum in a laboratory. The only other place we see them is in stars, right? So how in the world does this heated plasmatic gas at the beginning of the universe create a black body spectrum that cools over 15 billion years and then somehow gives us this temperature of 3 Kelvin, which is where it's measured at today? I don't know. And I don't know that anybody's really answered that. It's a bit troubling. So we'll look at that in detail in a second. All right. So these gentlemen who made this detection, their names were Penzias and Wilson. They were working at Bell Labs back in Homedale, New Jersey, I believe, right on the coast of New Jersey. Now, this is essentially what that CMB curve looked like. Now, what was perhaps really, really disturbing was how beautiful it was, actually. You might think, well, that's great, it's really reliable, but the thing is, when you take astrophysical measurements, let's say when you do the measurements of, let's say we took the black body spectrum of the sun, for instance, and I've showed this before. It's a pretty jagged line, actually. And this is the sun, right? We know it has a beautiful black body spectrum, but the measurements are still variable, right? The light is sort of flickering here and there. It's, the atmosphere can get in the way, its own atmosphere, right, can get in the way. So it's not this beautiful, like the error bars on this microwave background when it was measured were just pristine, like perfect. Like if you were to actually go in a laboratory and heat up, a piece of iron and do the black body spectral analysis, like that tight, right? Like almost perfectly controlled laboratory conditions, right? Which is, I think, should have been actually a bit unsettling. Because if we're thinking about something that's actually coming from the cosmos, we would expect it to be a little bit dirty, right? We expect things to have interfered along its light path and so forth. So people continued to investigate this. They sent up weather balloons to hone in on this microwave background. They eventually produced a satellite, which they called COBE, to go in near Earth orbit, I think about 60 kilometers above the Earth, and make measurements. And indeed, still really tight error bars. Beautiful, beautiful picture of this black body spectrum. Still believing this to be some remnant of the early days of the universe. Now, somebody had the idea, well, we should probably go and see if it's happening away from the Earth, right? So they designed 2 different experiments to do that. And of course, immediately after they launched the experiments, they reported, yep, we see it far away. So you think, okay, wow, this is actually something that's happening out there, not just around here. Now, there is some trouble with those later 2 satellites, though, once you start to look at how the experiments were designed. The first of them was called the Planck satellite, which was, both of these satellites were sort of stationed over at L2, which is that little gravitational point of stability beyond the Earth, so away from the sun, on the other side of the Earth from the sun. They parked the satellites there, and they tried to essentially measure the CMB. Now listen to this, though. The way that the Planck satellite measured the CMB is that it takes what it considers to be its own version of a black body up there, which is calibrated to be essentially at the same temperature that they expect the CMB to be at. And it uses this as a reference mode. So it has an antenna and so forth, but it points this antenna, let's say one portion of its antenna, at the reference mode, and it says, okay, I know the temperature of this because it has a thermocouple or something, right? And therefore, whatever radiation is coming off of this little piece of metal, my little reference black body, I'm going to compare that to what I see in the sky. And I'm going to compare these 2 values and see what I get. And so they make this nice map, sort of something similar to what you see here. Now, there's a problem with that experiment. The problem is that the only way that a black body gives you a true temperature in a laboratory is if all of the energy in that black body is being radiated away. How do you make sure that that's done? You have to insulate the black body from its surroundings. In other words, if any of the heat from the black body can conduct into the surroundings, then it doesn't radiate away heat, it conducts it. Like bodies prefer to convey heat through touch. Radiation is sort of a last resort. And so the problem was that this reference module was mounted essentially with thermally coupled to the heat shield of the device. So even though it may have been at 3 degrees Kelvin or 4 degrees Kelvin, whatever it was in thermal equilibrium with its shielding, and it was essentially able to convey away all of its heat. And so the thing probably had no black body radiation whatsoever. So in my mind, I'm like, I wonder if that experiment actually didn't just show that compared to a reference value of 0 black body radiation, that you have nothing actually. Now the second experiment, which I think this picture is actually from, is from the WMAP experiment. That one's actually even a little worse in its design. In this case, what they did was they had a differential radiometer. So what they did was they said, we know that the black body spectrum of the CMB, as detected back on Earth, has a temperature of this at this particular frequency spectrum. And what they did was they put a radiometer, so something to look for radiation, in both directions, 2 directions, so mounted back to back, and they said, go look for the difference in that temperature. So go find differences at 3 Kelvin in this particular power density, and this is the map they produced, right? So they didn't actually measure the CMB at either one of these experiments, which is interesting. The only place that I can tell that it's actually really been measured at is at Earth itself. And so this is going to become even more complex in a second. Now what they did measure at these experiments is a great deal of anisotropy, right? So for one, the galaxy itself is an extraordinary emitter of microwave radiation. So they had to actually delete the galaxy, which was the strongest signal from these maps. And once they deleted the galaxy from the maps, this is what they saw. And this is interesting. Now, initially, this was written off that the red parts and the blue parts were essentially the way that the Earth was moving with respect to the CMB. So there's going to be some blue shift as we move towards the CMB and some red shift as we're moving away from it, right? On either the back side of our orbit or the front side of our orbit. Now, the problem was that as people have continued to analyze this over the last 20 years, they've discovered that actually a lot of different structures in the universe are preferentially oriented with respect to this. And that the Earth's motion with respect to other galaxies, let's say, so if you compare our motion with respect to other stars that are very far away, so other galaxies, that our motion towards those stars and the other galaxies has nothing to do with this motion. So in other words, our motion with respect to objects we can see is not the same as our motion with respect to this static background, which really starts to bring up the question, what the heck is this anisotropy about? What is this actually showing us? And I have some ideas, and I'll put them out in just a second here. All right, sorry, this was just a quote. This is a quote from the WMAP project from one of the authors, which of course is saying that they're actually comparing these measurements they're making these measurements at L2 by calibrating them to what they know from near Earth orbit. So let's look at some clues about what might actually be happening. So I'm getting into a complete theoretical landscape here just to give you guys some idea of where I think that this is going to go in the next 20 years. I think that the problems with the anisotropy of the CMB are mounting to the point that it's becoming a little bit untenable for the cosmologists. And so the question actually, which always needs to be solved before people move on in a paradigm, is what in the world is causing this microwave background radiation in the first place? So, again, in laboratories, how do you make a black body spectrum? Got to heat up a solid or a liquid. So where in the world could we get a solid or liquid that would have a temperature at 3 Kelvin? Now that's really, really cold, by the way, which is a bit disturbing. It's really, really cold, so it's going to be tough to find anything that cold. Now, there's a couple of clues about this, and I know this is a ridiculous amount of text, but I think these are actually worth reading to you here. So one thing that's quite interesting, and my friend Pierre came across this, is that communication satellites, right, the ones we use for our cell phones and the military uses for all their space weapons and stuff, when they orient, when they calibrate the alignment of their communication satellites, they use the CMB, actually. Now, what's really, really, really interesting is you would think that if you were a comm satellite and you were calibrating yourself like to the CMB, where would you point your satellite? Anybody? To the cosmos, probably, like to the dark part of the sky, right? They actually aim them at the limb of the Earth. That's the edge of the Earth, right? So these comm satellites calibrate the CMB off of the limb of the Earth, which is really, really strange, actually. Sort of like this. Now, there's also this interesting history in all of these satellites where where the builders are constantly talking in the journals where they're building these different CMB experiments about how water is really screwing up their instruments really badly, right? Now, we know water is a really strong absorber in that microwave range, right? If you guys have ever used a microwave oven, you probably realize that your food doesn't get hot unless you pour some water on it, right? Water is extremely sensitive to microwave radiation. And remember, Stewart's law, right? Maybe we can call it part of Kirchhoff's law, that if something absorbs out of radiation, it also emits at that same frequency, right? So if water absorbs in the microwave, that means it also emits really strongly in the microwave as well. Now, there's also this really interesting phenomena regarding the polarization of signals. So you might think, okay, maybe water has something to do with this microwave background signature. But it's very bizarre that you would get a 3 Kelvin temperature because the water on Earth is pretty warm. Let's say it's in the 270 something, above 270. which is 0 freezing point as far as we're concerned. So the oceans are, probably 280 or more on average. So why in the world would water play anything to do with this? Let's talk about that in just a second. Now, there is this really interesting effect here, which is that if you measure a signal of water, actually, so if you take that CMB satellite that's measuring the CMB, like the COBE satellite, and you point it directly at the ocean, well, the angle down here, let's say the nadir angle, that's just like how far you are off axis from your target. When it's at 0, you actually get a very accurate temperature for the water that you're pointing it at. So you can get a microwave signal from the water, and it reads, something reasonable. But the problem is that as your signal moves off axis from that, the apparent temperature due to the polarization of that light actually goes down to the points that you actually get very close to 0 at some point. So if I was to measure the temperature of the ocean based on its own microwave radiation, I would get the proper temperature of the ocean, which can be measured checked with a thermometer. But if I turn my satellite towards the edge of the Earth, towards the horizon, all of a sudden the temperature of that microwave reading falls down very close to 0, very close to 3 Kelvin, actually. So what's going on? There's another piece of this puzzle, too, which I think is worth pointing out. So, they did all these nuclear bomb tests. You've probably seen some of them. They're quite horrific. But there's one piece of this puzzle that you might not have noticed, which is that when this explosion happens, there's this ring, actually, that travels outward in the water away from the source of the explosion. That ring is of optically opaque water, completely black. It's a black ring of water. You can watch these videos. There's a black ring that spreads outwards from the explosion points. Now, you might ask, what the heck is happening there? Well, the only way that a substance changes its optical properties is because the lattice inside of it has rearranged in some sense. Now, you might think, well, why would a liquid have a lattice? Well, especially water, right? Water has this incredible ability to hydrogen bond, right? So hydrogen bonding means that water is actually connected to its neighbor, but it's a very transient connection. There are these really weak bonds. So it doesn't get stuck in those conformations. It can move around and still have connectivity at all points, and it's quite strong. This is why droplets of water are held together, right? They're not actually, the shells of those atoms aren't actually wound up together like in a covalent bond, but they are stuck together. They're enmeshed. There's some sort of Velcro going on nonetheless. Now, what's happening in this picture here where you get this black water appearing? Well, something is changing about the hydrogen bonding network when that load is compressed extraordinarily. So what's happened is that water is usually transparent in the visual range, but it's actually opaque in a lot of other ranges. So if I was to take, this radio receiver and go dive underwater with it, or try to take a cell phone call underwater, it wouldn't work at all. It's actually, this was a huge problem for submarines, actually, in the early years of submarine warfare, because they had no idea how to communicate with each other. They would lose their radios even when they went as low as like a meter underneath the water, right? So water is completely opaque to radio microwaves and radio signals. But it lets some visual light through, unless the lattice changes of the water. When it's compressed by that nuclear explosion, something squishes together about the lattice, and it loses its optical transparency temporarily, right? The actual arrangement of those water molecules is changed in such a way that it can't relay that light signal anymore. So, the theory is on the table that the oceans themselves are actually under a great deal of pressure, right? That's a lot of water stacked up. And that the actual hydrogen bonding lattices of the ocean themselves, when viewed at that angle at the Earth's limb, might be capable of providing that black body spectrum that we've been perhaps mistakenly attributing to the cosmos, which is actually something very close to Earth at the end of the day. Now, if that happens, that's going to be one of the craziest moments in the entire history of science, because I'm not aware that anybody's ever been given a Nobel Prize and then had it taken back before, right? So those guys who discovered this microwave background radiation and the guys who interpreted it as the hiss of the Big Bang, they were immediately, well, actually took about almost 10 years. They were given a Nobel Prize. They shared the Nobel Prize for that discovery. Now, if it turns out that they were actually measuring water contamination into their horn and that several $1 billion worth of satellite experiments had essentially been honing in on the water contamination, that'll be a really interesting moment for the humility of science. I actually think it would be really, really good for us as a civilization if we could learn how to say, hey, it's okay, sometimes we're wrong about stuff, and sometimes we have to go back to the drawing board. Does anybody have any questions about this completely crazy theory that I'm putting on the table for you here? Yes?
So when these satellites are measuring like the sort of terminal visual points of the Earth,
The limb, yeah.
are they measuring the physical surface or are they measuring the atmosphere?
They're aiming right at the limb, right at the border of the sky, right?
Okay. So
And
they're pulling measurements from the surface of the water?
there's two possibilities going there. I think that what's probably happening is that they have a cone, right? The cone, this is why I tried to show you how that temperature goes down as you get off axis. I think what they're doing is they're still kind of pointing right past the edge of the Earth, but what's happening is that the ocean water underneath is leaking in at the angle from the side of the cone. So they're pointed, the side of the antenna is pointed down at the Earth, and we saw that actually the microwave temperature of water goes down precipitously. You get this artifact where as you turn away from the ocean that you're measuring, your temperature drops down to about 3 Kelvin as a result of it. So what's happening is when they're pointed off at the limb of the Earth, they're actually measuring the ocean below them off axis, essentially, which is giving them that nice 3 Kelvin microwave temperature, which is extremely reliable, and it allows them to calibrate their orientation that way, because it's always pointed at the same direction.
So that measurement is consistent even as the Earth rotates?
Yeah.
The Earth, I mean, it's mostly water, but not all water, so you would assume that at some point that same signal would be measuring the spectrum of the land.
Yeah, it's something like 70%. 70% of the surface is water, and of course those satellites I think they probably rotate on the order of hours, their orbits, right? So there's probably some smoothing going on there as well. But yeah, it's a reasonable point. I think that I think what like. I mean, I think that the real onus is like, I don't know if this is the correct answer. It's an answer that makes sense to me. I'll tell you what doesn't make sense to me is that you could get a gas to give you a black body spectrum, period. So if the answer is that this is a cosmic microwave background, maybe it is, but I don't think that the experiments have shown that it's cosmic in nature. And I definitely am not buying the argument that it has anything to do with gaseous plasma from the beginning of the universe, because no one's ever been able to do that. Like, I'll completely surrender, and I'll be like, absolutely great if you can show me one experiment where someone's taken a plasmatic gas and derived a black body spectrum from it. It's never been done. In fact, these gases give a very, very specific signature, which is individual line frequencies. So both the argument for what it means and its cosmic origin are a little bit on the ropes as far as I can tell. And the fact that these different anisotropies appear that seem to be correlated to our own motion, let's say to our own solar system location, that they don't seem to align with our motion through the galaxy, they seem to be really local to where we're at. I think that at least points to something being really off about this being a cosmic phenomenon. So, I don't know that we've come across the answer yet. It could be the oceans. That certainly would be capable of giving a black body spectrum at the proper temperature. But I can't think of anything better. But maybe there's something else to it too. And if it is shown to be cosmic in origins, it still might be a water story as far as I can tell. Again, water is, as far as I can tell, the most abundant and powerful microwave absorber and emitter in the universe. And there's a lot of water everywhere. So maybe there's something to that. But it would have to be a condensed form of water. It wouldn't be a gaseous form of water, because gaseous water would, of course, give line spectra as well. So it wouldn't be just like little molecules of water. We're talking about some body of water. Now, even in our own solar system, there's a lot of bodies of water, though, right? We have these subsurface oceans on dozens of moons throughout the solar system, so plenty of opportunities for it. So anyways, I realize this is pretty out there and heretical, but I think it's an interesting complement, a nice piece of your food, let's say your food pyramid to complement the textbook. I do think these theories are on the move. I think we'll have a very different story to tell 50 years from now. I won't be here, but somebody else will be telling a very different story. And maybe this is where it's headed. So Thursday, I want to move towards perhaps talking about other cosmologies and the way that people have seen humans' place in the universe with respect to the story of this place that is in some sense congruent with the way science has seen it, and in some sense at odds with it. And maybe we can get a sense for where cosmology is headed in the future as a result of that. So guys, if you want to come early to class on Thursday, it'll be the last time to hang out. It's going to be our last class, sadly. And yeah, if you have questions, make sure to hit me up this week. And good luck with getting ready for your finals and everything. And I'll see you guys Thursday.